Could be Ayush. Yeah. Okay. So right. So where we are? Another round of coffee. That's okay. Maybe I can take a break in the middle and get a coffee. So today is lecture 18, and I'm thinking so partitions, two more lectures at least, and then rest we can do some symmetric functions. So I found a nice book on it. I'm just looking at it. If it's okay, then I'll tell you the reference. It's one of those, uh, AMS book, student studies. So it's got stuff very nicely written. But there's a very famous book by an Indian author called V. Krishnamurti. So I just have to compare the two and see whether VK is better. So V. Krishnamurti is really very nice book, and it's he was in BITS Pilani, and he used to teach Combinatorics over there, and he has a very nice book. It's very old, but it's very nice, and it's available for free, so it's okay. I mean, the other one is also you can sort of steal. Anyway, so let's begin. So this is recall. This is still continuing some joint work with Hartosh Singh Bal. Did you Google him or not? Do you guys Google him? You don't do your homework, huh? Did anybody Google him?
I don't think so, Professor.
Looks like. Well, I told you Google him. You'll be.
Looked him up a little bit.
What do you
Found
find
it hard
out?
to find some math stuff, though.
Huh?
He's a political editor of the Caravan magazine.
Yeah,
A
he's
lot of
a.
politics stuff.
Yeah, he writes on politics mostly. So, but he's quite a famous chap. Um, anyway, so recall that FK of n. So his story is that Hartosh's story is that he and I were in high school together. So we did our high school together, and then he uh, uh, he went to BITS Pilani, and I was in Delhi University, and then we both went to the US at the same time to study math. But he didn't finish. He went to NYU, but he didn't finish. He's a mechanical engineer. And then he was basically what is called ABD. ABD is all but dissertation. So all but dead or all but dissertation. So he left his PhD and then he became a journalist. And he's quite a famous journalist. And recently he wrote a book on logic in mathematics, a sort of mathematical novel. So he has been trying to get into math back. And then a few years ago, we started talking to each other and we did a paper together. Now we did another paper. Now we're doing another one. So so whatever I'm presenting here is actually coming out for the first time. So I've taken your permission to upload them on YouTube, but probably I will upload them only after I've submitted the paper, because of course there's nothing really new that we'll be presenting, no new theorems, but this technique is new. So then after that, if the paper does well, it might be these lectures will be even more useful for people who want to try that same method and do other things. So anyway, FKN is the number of occurrences of K in partitions of N, so frequency. So some of the frequencies. And we had this kind of matrix equation, Fnn is equal to this matrix times p of n minus 1 down to p0, and this matrix was all ones, then 1 0 1, then 0 0 1, 0 0 1, so on and so on. So and in addition we had this equation npn. So this is an and these two together, these two equations together, A and B, they determine P of n. So this matrix is the important thing. After this matrix and P0 equal to 0, if you just take this initial condition, then it determines all F's and N's. And so it's really strange. This is some number theoretic matrix, and this is what you get. And once you see why you get it, then it's okay. It's not so tough to understand, but that's the essential starting point for our paper, that we found this matrix to be very, you know, weirdly, this is a number theoretic matrix. This is like when I divides j, then you have 1, otherwise 0. So there's some divisibility property here, and this is an additive function. This is a function involving plus, number of ways of writing plus, and this is something which involves multiplicative number theory. And this is something else which has not been studied too much, except for one particular theorem, the Stanley-Elder theorem, which we did last time. Okay, so here's a general proposition, which we sort of mentioned last time, but let me just write it down. So let n equal to 1 to infinity be a sequence of n cross n matrices let xn for n equal to 0, 1, 2, so on, and yn for n equal to 1 over kn. Be related as follows. A of n is equal times x of n minus 1, x of n minus 2, and so on up till x of 0 is equal to y1 of n, yn of n, just like above. And summation yk of n is equal to n times, well, I don't need n times, I need just xn. Then given an initial condition x0, we can determine um, the xn and fk of n for y is coordinate fk, so and y of n for k equal to 1 to n for all n bigger than equal to 1. So the proof is quite easy. If we know x0, so let's call this 1a and this 1b. So if we know x of 0, x of 1 up till x of n minus 1, then using 1a, and we know a, we know this matrix, A. So whatever the matrix actually, it doesn't, as long as you multiply it and you can determine it, uh, then using 1A. So we are using very special kinds of matrices, but whatever the matrix may be, if we know x0 to xn, then using 1A, we know ykn for k equal to 1 to up till n, and then using 1b, we know xn plus 1, xn. So then we can extend this, then continue. So once we know n here, xn, then I can get y1 of n plus 1 and so on. So this is a very simple example, and in our example, we actually took, so we had a, so we had this a 0 1 0 1 0 0 1 0 0 1, and then we had this p of n minus 1 till p0, and we had a f1 n and fn. So what we did was we took uh, this guy. So we got this fn over here, but if we multiply by one this thing vector here, then I will be multiplying so on up till nn, and then the summation of kfk will give me whatever p of n. So here I'm just taking the sum of these guys, but here I took this matrix actually. So the actual matrix that in this general theorem that we took was actually 1 1 1 1 and 0 2 0 2, then 0 0 3 0 0 3, and so on. So we can multiply by something in the matrix and still get this, but the fundamental matrix remains the same. Okay, so this is the general enumeration result, and let's do one quick application to see the connection with number theory. Any questions?
So,
Yeah.
just a kind of observation. So, our matrix of ones and zeros that we have, if we take its transpose, then that gives us like the position of ones in the ith row will give like the divisors of I.
Hmm. I mean, are you okay? I think I know what you're saying. Just hang on.
Yeah.
Okay. So this is a recurrence relation I'll find, um, which is due to Ford, but I mean, it's not clear who it's due to. Some places they mentioned a name called Ford. So let sigma of n be what Ayush just mentioned, the sum of divisors of n. Okay, and then the theorem is npn is equal to the sum of sigma of d, p of n minus d, for divisors going from 1 to n. Okay, so the proof is as follows. So we have this kind of, we have this equation and so on. And p of n minus 2 and so on, p of 0 equal to um, f1 D, and I'll multiply by 2 here. So 2F2D and NFND. Right. So the sum, what is the sum of entries of the dth column of this matrix of A of n, let's say. So this is up till n, it goes. So what is the sum of the dth column? So this will be the sum of all the divisors of 2, divisors of 3, and so on. Because you're going to get a term like only in the 0, 0, 3. So 1, 2, 3, 4, 5. Sorry. So in the sixth term, you will get all the divisors of 6, for example. Just think about it. It's the entries of this matrix are aj aij is equal to the I if j is equal to or let me put it r. So I'm for some reason I want to use this notation a sub I of j. So this is equal to if j is equal to I times r, right? Then there is a non-zero entry. That means when I divides j, and this non-zero entry is going to be I, the row, and otherwise it's 0. So if you sum over all these guys, uh, you will get sigma of d for d equal to 1 to n, right? So what you do is you compute the left hand side, right? So you compute this times this, and so on, and then add up all the entries. What will you get? So if you calculate the left hand side and sum all the whatever you get, all the elements in every whatever.
Professor,
Yeah,
on the right hand side of a matrix equation, shouldn't it be a f1 of n, f2 of n, and so on?
yeah, right. So on the left hand side, you sum up all the entries, you'll get basically what we will get is we'll get sigma d and then p of n minus t, d going from 1 to n. Is this clear? Is this obvious? If I multiply this guy with this guy, I will get the n. I'll get the second term, then the fourth term, and the fifth term. Then I add all of them again. So if I just keep n minus d as a common point, I'll get the sum of divisors of d. And on the right hand side, if we sum up all the entries, we are going to get summation k f k n, which is npn. So if we compare the two, we'll get sigma d p of n minus t equal to npn. Is this clear? Does this make sense?
Yes, Professor.
Okay, it's kind of obvious if you just think about it. If you just take this entry, whatever you get, the coefficient of p of n minus d will be either 0 or it will be, d, depending on whatever, uh, whether there's 0 here or there's a d here. And it will be d only when it's a divisor. Okay. So, so that's a famous recurrence actually. So Erdős used this a lot to calculate stuff using P of n. So it was Erdős's favorite, and somehow this FK was not showing up in Erdős's work. He just hid that. He would just write this thing, and then he was using this. Anyway, so what we want to do is I want to give you today a calculus on how to write the matrix. So uh, to write down the matrix for all types of partitions. Just to see what we get, what A we get. So now we know what are the ordinary partitions. And what we do is we will always use the same symbols. So let A be the matrix with the first n cross n rows um, is this AN. Uh, so, and its entries are denoted AIJ. I mean, I'll give you a lot of, we look at a lot of partitions now, several partitions, one after the other, and all of them will denote by P of n, will denote whatever partitions we use. And we will use this symbol Rk of n uh, to give the generating function for the kth row. So it's n bigger than equal to 0. So the generating function of the kth row, and I'll use q q, which is for generating function of the partitions, uh, whichever one we consider in depending on context. I mean, otherwise we'll run out of a lot of symbols, so we're just using the same ones. And I'm using this term nkq as a generating function for fkn q raised per n. So one notes that so the frequency, I mean, if we have a frequency k of n, it's 0 if um, n is smaller than k. So if n is smaller than k, then uh, there is no k in its partition. And the k equal to 0 case we sort of ignore for a while because somehow it doesn't show up. So somehow k equal to 0 case does not show up. So in our calculations, but p of 0 we use without any p0 equal to 1 always works. Okay, so first let's just do ordinary partitions again. These are the usual partitions, and here q of q is this product k going from 1 to infinity or 1 over q infinity. Okay, and here we saw fk of n is equal to p of n minus k plus fk of n minus k. So this is for k bigger than equal to 1. So if you recall, this came from, you add xk, the symbol xk, to uh, partitions of n minus k, and these are the ones which are already there. These are the k's which are already there in partitions of n minus k. So then this recurrence relation holds. So what we do is I'm just going to get a sort of standard way of getting the answers from here, which is very easy. So earlier we did telescoping and something, we just guessed the answer, but now I'll just give you a generating function approach. So if you multiply both sides by q raised per n and sum over n, so on this side you will get fkn q raised per n bigger than equal to 0. Here you'll get q raised per k, sum p of n minus k, q raised per n minus k. And here you'll get f k n minus k, q raised per n minus k. So I take out, I'm multiplying by q raised per n, but I take out a q raised per k. And here I am again taking, I take p of negative to be 0. So that things work out. And here also we are taking, when k is less than n, when n minus k is less than k, then it will be 0. So it works out. Okay, and then this gives us nk of q is equal to q raised per k, q of q. So this is the generating function for this guy, plus q raised per k of nk of q again. And this means that nk of q is q raised per k over 1 minus q raised per k times q of q. So your generating function for the rows is simply q raised per k 1 minus q raised per k, and that's 1 plus q raised per k plus q raised per 2k and so on. Right, so this is what we got for the kth row. You got ones at the kth stage, 2kth stage, 3kth stage, and so on. So aij is equal to 1 if I divides j and 0 otherwise. So this case we had already done. Okay. And this approach is with generating functions. It's quite easy. It applies to other types of partitions. So now I want to discuss a sequence of partitions, which will give me a sort of, yeah.
So, Professor, how did we get RK of Q?
Well, um, um, I mean, if I okay, hang on. So I have this guy, and I want the generating function of this chap, right? This is the kth row, and this is Pn and so on, Pn minus 1 up till P0, and then this is F1n, F2n, and so on. So what I need is that I want the generating function for this particular row. Um, what am I doing? I'm just uh, okay. I haven't even thought about it for a long time. So let's just figure it out. So what am I doing? I'm just multiplying by. So this is let's say this is AK1, AK2, and I'm multiplying this by 1 q, q square, and so on. No. Uh, so I want, how do I say this? It's kind of obvious. Okay, forget it. Let's try again. So whatever I've got here, it's AK of 1 times P of n plus AK of 2 times P of n minus 1, uh, P of n minus 2 plus AK of 3, P of n minus 3, and so on. And that will give me the kth guy, Fk of n, right?
Professor,
Now
isn't it
I,
KFK of n?
sorry.
Isn't it KFK of n?
No, right now let's just keep it at ones. Uh, I mean, let's just keep the usual ones. So this matrix is just one. If I dividing j, sorry, not I. This is just the ones matrix. Okay. Okay, thanks. Anyway, so now look at this side. So now what we are looking at is Fk of n q raised per n, and this is a convolution. So this guy q raised per n. So what is this? This is the convolution. So this is a generating function for multiplying the generating functions of uh, the r and the q. Yeah. So this is a convolution, right?
Professor,
Yeah,
is
yeah.
AK of 0 is AK of 0 taken to be 0 conventionally?
It doesn't show up because somehow we don't have an AK of 0.
So I couldn't get it.
So this matrix is indexed by 1, 2, 3, so on up till 1, 2, 3, so on. That's it. So there is no a. So this is the kth guy, and this is 1. This is kth guy, which is 2. So 1 is multiplying with p of n minus 1. That's all. So there's no 0. AK of 0 doesn't exist. Well, I mean, you can call it 0 then, of course. Sure, sure. I get you. Okay, I got what you're saying. So you could just say, sorry, RK, this is the RKQ is summation AK uh, J Q raised per J, AK N Q raised per N. So N going between 0 and, so you could say that, but it's actually, so yeah, you can take AK of 0 to be 0. I mean, it never shows up, so it's okay. Okay, is it clear now? Or have I confused you guys further?
It's clear,
Is this
Professor.
okay? Is it okay?
I think I missed the last step. Like after the convolution, I think I missed what you said.
Okay, so this was based on your question, what should we take AK of 0? So I guess yes, you can take AK of 0 to be equal to 0. It doesn't show up in our matrix ever. So when I write formally the generating function over all n, I could take it equal to 0. So the generating function, I mean, what is the generating function of the first row? It's going to be 1, it's going to be q plus q square plus q cube plus so on, the first row. Because q raised per 0 doesn't exist and my indexing starts only with 1. So yes, you could take AK0 equal to 0 if you wish. This is row 1. So row 2 it starts with the second guy, and then q raised per 4, then q raised per 6, and so on. And this is exactly what we got. We got Rk of q as q raised per k over 1 minus q raised per k, which is q raised per k plus q raised per 2k plus so on. So for k equal to 1, it is 1 plus 2 plus 3. For 2, it's 2 plus 4 plus 6, and so on. Okay, is that okay? Shall I go on? So the confusion is here. I mean, it's 1, but I wrote it I.
Professor, can you, yeah, can you,
Can I?
yeah, so Professor, we are getting, on the right hand side, we have summation fk. Oh, okay, so we have fk, we are getting fkn from the product rk of q and q of q, and then we are multiplying that by q to the n and summing it over n.
Right, right.
Okay, yeah, that makes sense.
So this is what you get. Then when you sum over it, then this is what you get. And then this will be a convolution. So that's why you get it. Okay, so I hope that's clear now. So thank you again. This is something which I didn't even think about for a very long time. So I thought it was obvious, but maybe not. So anyway, let's try partitions with odd parts. So again, let us use Pn as P of n with all parts odd. Let's just use this. And let's just use Fkn is the same frequency function, and Q of Q this time is little different. So only odd terms are over here. So this is Q square infinity, right? So we are only taking partitions with all parts odd. Okay, so let's just let us list them, list a few just to gain some intuition. Okay, so for n equal to 0, so these are partitions with odd parts, and I'm going to use x's again, even though I asked you to use a's. So n equal to 1, you have x1. X equal to 2, there's 2x1, but if I use x2, that's not allowed because I cannot have a partition with an even part. Okay, so let's do 3x1. X3 is okay. You have 4x1, you have x1 plus x3, but x4 is not allowed. This is not allowed, right? And obviously we can't have 2x2 because x2 was not there at all. So 5x1, then 2x1 plus x3 is okay. X2 plus x3 I don't have because x2 is not allowed. So there is x5. Let's do one more. And x6 is not allowed. But you have 2x3, so that's okay. All right. So x6 is not allowed. So how many are there? Just make a list. So it's 1, 1, 1, 2, 2, 3, and 4 here. Right. So what is happening here is that one thing to note is that if fk of n is 0 for k equal to 2, 4, 6, and so on, right? And otherwise we are the same. Otherwise it satisfies the same recurrence. So for k even, this is there, but for k odd, we are adding xk to the kth guy if it exists. So p of n minus k plus fk of n minus k for k odd. So k equal to 1, 3, 5, and so on. So it's the same recurrence relation. However, there is no even terms in the recurrence relation. So what is the matrix? It's the same matrix except there are no even terms. So the matrix is 1, 1, so on. There's nothing here. This one comes up, nothing here. Then fifth one you'll get something, and so on. Right? So the matrix is the same as earlier, but rows are deleted. Even rows are 0. So let's see how it works. Let's calculate first. So the formula I'm writing, Aij is equal to 1 if I is odd and I divides j, and 0 otherwise. Okay. So let's try it. So P0 is 1 as usual. In the if we do n equal to 1, so I will just get 1 as a matrix, P0 equal to F1 of 1. So 1 times 1 is equal to 1. So F1 of 1 is 1. And P of 1 is also equal to 1 times this, which is 1. So we got 1. So next one we have this matrix, and this is going to be F2 of F1 of 2 and F2 of 2. Okay, well, maybe I should write it the other way around. 1 and 1. So this is 2, this is 0. So F1 of 2 is 2, F2 of 2 is 0. And what do we get? We have 1 times 2 plus 0 times, 2 times 0 is equal to 2 times P of 2. So P of 2 is equal to 1. Okay, let's do one more. Do you remember we were doing this for the ordinary partitions last time? 1, 1, 1, 0, 0, 0, 0, 0, 1. And now it's 1, 1, 1. So the first guy gives you 3, second guy gives you 0. So obviously, I mean, F2 of 3 has to come out 0. That's why the second row is 0. Because you can't have any partition with 2 as a part, with even part. So that's has to be 0, and the third one is 1. Again, so F1 is this, F2 is this, and then 1 times 3 plus 0 times, 2 times 0 plus 3 times 1 is equal to 3 times P of 3. So that will give you P of 3 equal to 2. So this is what we got. 1, 1, 1, 2. We can do one more if you wish. So F1 of 4, F2 of 4, F3 of 4, F4 of 4, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. This is equal to plus 3, 6, 8, 2, 1, 1, 1. So what do you get? 2 plus 3, 4, 5 here, and then 0, then 1, then 0. And what is P of 5? That is 1 times 5 plus, no, this is P of 4 we are getting, sorry, plus 3 times 1, which is equal to So this is 4 times 4. This should be equal to 8. So P of 4 is equal to 2. And this checks out. So 1, 1, 2. So essentially, once we figured out the matrix, we get all the numbers just from the recurrence relation. Okay. And any questions on OR? So the goal is to find the matrix, and here we just say that the matrix is with the even terms deleted. And the remark is that uh, for partitions with elements in a set S. So if you're just doing 1 over 1 minus q raised per s for s belonging to capital S, this is the generating function for partitions with elements in a set S. Then the matrix A is basically easy to find. It's Aij, and this will be equal to 1 if I belongs to S and I divides J, and 0 otherwise. So for example, we'll see an example of Rogers-Ramanujan identities where we have this kind of matrix. 5k minus 1 and 5k minus 4. So k going from 1 to infinity. So basically, you'll have k equal to 1, so 1, and k equal to 2 is k equal to 1 here is 4. So 1 and 4 mod 5. So 4 and 1 mod 5. This is generating function of partitions with parts 1 and 4 mod 5. I'm going to 1 and 4 mod 5. And the matrix is easy to write. So matrix has got zeros unless, so same matrix, but zeros at all other places. So 1 is okay, 2 is not okay, 3 is not okay, then 4 um, you'll get 1, 2, 3, 4th you'll get something, and so on. So matrix will be easy, and then you can generate the partitions. Okay, so that's the remark. Uh, Type 3. Okay, so I mean, it's getting there somewhere. Mm, trust me, it's a little this thing, but so partitions with distinct parts. Okay, again, now q of q is equal to 1 plus q raised per k, which is minus q infinity. So we've seen this, k going from 1 to infinity. Let's just list a few again. So, when I'm working in this area, I do this every day. When I begin the whatever object I'm starting, I'll just start listing, and when my list reaches about 6 or 7, that is when my brain starts working. Okay, so I can't have 2x1. So 2x1 is not possible because it's distinct parts, right? But I can have x2 here, right? And then I can have x1 plus x2. I can have x3. I can have, so I'm just adding 1 to these guys, but I can't add to this chap. I can only add to this guy. And I have x4. I can't add x2 to this. So 2x2 again banned because it's distinct parts, right? So again, I can add 1 x1 here, but I can't because it's already there. So I can add x1 plus x4. I can add x2 to this chap. One step before, I can add x2. This guy is okay. and then I need an x5, and then I'm done. 6, I can add x1 plus x2 plus x3. I can have x1 plus x5. I can have x2 plus x4. I cannot have x3 plus x3, but I can have an x6. So these numbers should be the same because we have a theorem of this kind, right? So the numbers should be same as odd, previous case, because we have a theorem that odd equal to distinct, right? Is that okay? So how do we get this thing? So F1n is basically I add 1 to the previous guys, but I subtract the guys which are already there. So I can't add, I add 1 to this chap, but I can't add if it was already there. So I add only to this and this. That's the basic trick. And same thing with F2 and Fk n is also the same. So I add an n, I add an xk to everything k steps before everything. So I don't worry about whether I had done it before or not. I add it to everything, but I subtract the ones which already are there. So this is Fk n minus k. Right, so we have the same recurrence except instead of a plus there is a minus. Right, so let's solve it. So multiply by q raised per n and sum over n. So here we'll get fkn q raised per n over n is equal to q raised per k minus q raised per k summation fk n minus k q raised per n minus k. And this will give me, so we are still using the same notation with a different value nkq. So this will give me nkq is equal to q raised per k over 1 plus q raised per k this time. So our kth row generating function is given by, which is q raised per k minus q raised per 2k plus q raised per 3k. So what is Aij? It's the same matrix except with alternating signs. And so on. So this is the matrix, and Aijth term would be defined as, so I mean it starts with 1, so let's say I is equal to j equal to, so the jth column, if it is if I divides the jth column, this is what you should get. Right, so let's just look at it. I mean, we're starting with 1, so r equal to 1, so j equal to 1, it's a plus sign, then j equal to 2, it's a minus sign, and because it's 2 minus 1, right, and so on. And similarly over here, I is 2, so j equal to 2, you'll get a plus sign. Is this clear? Okay, so just try out a few. Just try a few calculations just to see if an p of n minus 1 and so on equal to f1. Just do 1 or 2 by hand just to see if the first few terms are matching. So the remark here is, this is remarkable now. This remark is that the matrix is very different from the one for odd, for generating odd um, partitions. Yeah. Um, I mean, if you look at the odd guy from a linear algebra perspective, I mean, there's some zero rows which don't happen in a normal so the rank is smaller if you chop it off. And with these distinct, this is like a pluses and minuses type of thing. So this is a very interesting and this is very nice matrix compared to this one for sure. And the matrices are different, but they generate the same numbers. Okay. So try a few, and my suggestion is maybe an exercise in the next homework is to write a program for to enter A, values of A somehow, and output Fk of n and P of n, some kind of program to just implement this idea, to do that. And one can just I mean this calculus which I'm doing will basically tell you that if I take with any partition type thing, how does one get a matrix? But this should be this should be an important part of your thing. Okay, any questions?
No, Professor.
Okay, if you don't mind, I'll go and get a coffee in 1 minute. It's already made. I'll just get a coffee and come back. Okay, I'm back. Sorry to make you wait. Okay, so the next thing I want to do is I want to refine it. I want to refine this counting, this matrix, and to count the number of parts of the of a partition. So in this case, let me use this notation now. So I said I'll use the same notation, but I sort of changed the notation. So here it is m parts. I'm not doing k parts because I'm doing this. And now I have a new generating function, p and z, which is summation p n m z raised per m. Okay, and we have if we let's call q is the same, but I'll add a z over here, and this we had already seen the generating function. So we have something like this, right? So this was 1 over zq q infinity. So the powers of z keep track of the number of parts, right? And we can use this as it's a two variable generating function. We can use this to keep track of the parts itself. Okay, and uh, we say that for n bigger than 0, pn0, that means number of parts 0 is going to be 0 for this, and this as a convention we say it's 1. So p0z is taken to be equal to 1. So this P0Z acts like our P0, small P0, which we were earlier doing. So this is capital and this is small. A little confusing, but it's a partition function. I mean, this thing acts like, in our previous story, this acts like P of n. Okay, I mean it's analogous to that, whatever this polynomial is. So it's a polynomial, and now let's list them. First thing we do is list to get any kind of intuition whatsoever. So in the beginning part of the course, I didn't do so much of listing because we were just going ahead. But mainly it wasn't. I mean, it's not my area even. So I'm a little lazy to list those things. But in general, any combinatorial object that you see, in fact, even for any other mathematical object, you should basically just list and see for small cases what it is. People don't do it, and then they just keep, they keep going into this abstract thing. So this guy Nishad, remember Nishad? He came for our seminar.
Yes, Professor.
He gave a talk on graph theory. I don't know. I don't think everybody was there, but Nishad came. So Nishad and I were postdocs together. I mean, I've been out of math, so I was sort of an old postdoc. He was a young postdoc, but I had, both old and young can have beer together, so it's okay. So Nishad was referring a paper, and he said it's all this huge proof and all that. I said, have these guys? Do you know that these guys have verified on the computer or not? And they're computer scientists. So then Nishad told me, no, they haven't verified most probably, and it's too complicated to verify this that. He says, I verify, I'm very good at it, this that, but I don't. So then I said, okay, let me bet that you'll find a mistake there. So then he got really upset. He said, no, 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 that's not how it happens in graph theory and so on. But it so happened that he found a mistake because people didn't work on the computer. I mean, they're computer scientists, in fact. They're not even, I mean, they're in the computer science department. So they're mathematicians, and they didn't use a computer to verify what they were writing. So steps of the proof one can verify to make sure that you're not fooling yourself these days. It's very, very different from, it's not very different from times of Gauss and Jacobi and Ramanujan and so on, because it's possible to do. It's not impossible not to do. And scientists do that. I mean, physicists and engineers and all, they regularly just check their stuff on the computer if it works. I mean, they go the other way. They will not give a proof, and they will say it works. So, but for a mathematician, one has to do both. Anyway, so first thing one has to do is to list everything, every object, whatever we're doing. Anyway, let's do it. It's not so much of a big deal. So now the partitions are going to be some polynomials. And here I'll just calculate P and Z. So this one is 1, P0 uh, over here. So for 1, I just have x1, and I keep track of the number of parts. And this partition is going to, or we'll go to that later. Now, if I do 2x1, x1 plus x1, then there are two parts. So I do 2 square. And if I have x2, there is just one part. So I keep z here. And then 3x1 is z square. And then x1 plus x2. And now we have two parts. So 3x1 is z cubed, sorry. And then x3 is one part. Do you see what I'm doing? I'm just adding a z, a power of z, to keep track of the number of parts. Each time I add something, I'll increase the number of, I'll increase the power. So each time, so if I add a 4x1 here, then I have to increase the power by 1. If I add an x1 here, it's 2x1 plus x2. I have to increase the power to z, and again x1 plus x3, z square, Now 2x2, again I'm increasing the power here, z square, and then 0, x4z. Yeah, so is this clear? Is this clear? This fine? Okay, now what is PNZ? PNZ is PNN, number of partitions of n of this part, number of parts. So there is only one partition for one part. There is one of each here, right? So number of parts is 3. This number of parts is 1. Number of parts 2, there is only one partition. Number of parts 3, there is only one partition. Here, I will start getting something. So there are two partitions with two parts, and there's one with 3 parts and one with 4 parts. So I'm keeping track of the number of parts in this guy, and I'm listing the partitions over here. And what is my recurrence relation? The recurrence relation is pretty much the same. Uh, Let me call Fk, instead of Fk, let's call it Fk hat, and there is an m here also, so it depends on n and m. Okay, well, let me just put an m here. This is the number of times k appears in a partition of n with m parts. Okay, and from our story, it's clear that it is, you take n minus k m, m minus 1 part. Each time we are adding a z to it, and whatever was existing there earlier. So same kind of recurrence relation, and let fk of z and n both be this sum fk hat of n m and z raised for m. So we're keeping track of the m now, right? So m going from 0 to n or 1 to n. Okay, which we call this. So we call fkzn the frequency polynomial. Earlier it was just a frequency. Now it's a frequency polynomial. So from this guy, if we just sum over, okay, we also need this notation. Nk of zq is the generating function of fk of zn, q raised per n over n. Okay, so from star, we immediately get fk of zn. So just sum, multiply by z raised per whatever, and then sum. It is z times p of, I think we had n minus k. What was the, yeah, n was in the denominator, and z plus uh, z square p of n minus 2k z. So so all these guys, I'm adding, why am I getting z minus? No, I'm just getting z. So if I'm just taking z raised power m and summing over z, I'm just getting z of fk of n minus k. Sorry, z n minus k. Is that fine? So I'm just multiplying both sides by z raised power m and then summing over m. And this is what I will get. This was my notation for fk, z, and n, putting both of them together with a z. And then this will give us, so now I multiply by q raised power uh, n and sum over n, and then this will give me nk of zq equal to z times q raised per k of q. I think the notation was q cq, and this will give me zq raised per k nk of zq. Yeah, is this fine? So I'm multiplying by q raised per n and summing over all n. I'll get this. And from here I will get, so this is n minus k, so I'll take a q raised per k outside like I did earlier, and then sum over n, and I'll get q of zq, and same thing over here. And this will give me that nk of zq is equal to zq to the k 1 minus zq to the k. So again, we have got a generating function for rows very similar to the earlier guy. Let's call it rk of z and q, and that's z to the qk and 1 minus z to the qk. So what is the matrix? I'm adding a power of z to each column. So ai of j is equal to, instead of 1, I have a z raised per r for if j equal to r times I and 0 otherwise. So um, this is the matrix. So when I had at I have a z square, z cubed, and so on. And then here I have z square, z cubed, and so on. Z raised per, so the second term will be z square, and then 0, 0, z. So very, very similar to the previous guy, except you have these guys which take care of the parts. And further, we claim that this kind of situation also works. So fkzq, we had zn. Over k going from 1 to n is equal to n times p and z. Okay. So proof of this claim. I mean, up till here is fine. Is it? Is it? I mean, it's the same thing repeated once again. Okay, so uh, so the proof of this claim. I mean, this is easy. So for any partition pi of n with m parts, with exactly m parts, let fk pi be the number of k's in pi, the frequency. Then same proofs basically work. K times f k of pi is equal to n, because I mean that's the meaning of the partition. And if you sum over all partitions pi with m parts, right? And then you get the coefficient of z raised per m in k pk zn. You get the coefficient of z raised per n. And on the RHS, you get n times p of nm. So then you multiply by z raised per n and sum over n, you get the result. So then result follows, the claim follows. So I mean, we just take the partition of n into m parts and do the same thing as what we did earlier. And what we get is the coefficient of this polynomial, of this partition polynomial, whatever it is. Okay, any questions on this? So again, if you want, you should try a few cases and see whether we're getting the same numbers as here. Are we getting the same polynomials now as over here? So it works actually. It's quite nice. It works with polynomials. So try means, it's an exercise. It will show up. Okay. Well, there are two more or three more, but we'll do some next time. So similarly, I'll say similarly, for partitions with distinct parts, right? And the details are exercise. You take QQ to be equal to product of 1 plus QKZ, where K is 1 to infinity. So this is minus QZ Q infinity. Okay. And it turns out that Aij will be equal to minus 1 raised per r minus 1 and then z raised per r if j equal to ri and 0 otherwise. Okay, and now if you want to change, so any questions on that so far? So number 6 would be you change signs. How do you change signs? So suppose you have QQ equal to k going from 1 to infinity 1 over 1 plus q raised per k. So this is possible now. I mean, you want to find out. So this was a Euler thing, right? Suppose I want to change the sign. So this we know 1 over QQ infinity. I know the thing. What happens to to minus Q? I know this guy. And this is easy to
So,
get by, yeah.
so, Professor, what do we mean by change signs? Change signs of what?
So I mean, I have this 1 over. So I know the partitions. I know how to enumerate partitions of 1 over 1 minus q, 1 minus q square, and so on by the first case. So instead of that, I do 1 plus q, 1 plus q square, and so on. And similarly here, I know the partition of distinct. So I know 1 plus q, 1 plus q square, and so on. What does it? How do I generate for 1 minus q raised per k? I mean, this came up in Euler's pentagonal number theorem, right? This product. So yeah, to answer your questions, we know how to write A for 1 plus q, 1 plus q square. That's the distinct case. Yeah. Now, how do we write? So what is A? So question is, what is A for 1 minus q, 1 minus q square? That's what it means by changing signs. And the answer is immediate from part 5. From part 4 and 5, you take z to be equal to minus 1. So just to write down the answer for this guy, aij will be equal to, so you replace, over here you replace z by, you're replacing z by minus 1. So if you do this, then you're going to get minus 1 if j equal to ri and 0 otherwise. So this is your Euler pentagonal number case. The matrix you're going to get is minus 1, so on, and 0, minus 1, 0, minus 1. I mean, all the matrices are basically, they're variants of the same I, and you multiply by something and divide by something. This is the, I mean, this is the thesis. Okay, so I'll leave something for next time. Uh, one thing is pending. What happens if you multiply two generating functions? So I've got all kinds of these products. I've got these products zq infinity, 1 over zq infinity, for various values of z, 1 or minus 1 and so on. What happens if you multiply both of them together? Then what happens? So let's assume, so there's an example. So for example, which we will do next time, q bar of q, it's this kind of thing. What does this generate? Okay, this is something called over partitions. Okay, and we'll do them next time. So the point I'm making is there are a lot of, so here's the point. The point is there are a lot of partition-like objects in this universe. And what we want to do with this calculus, whatever this calculus was doing, the calculus is to find A for all of these, for these kind of objects, for all these. And let me say that at some point we can even, in Wilf's book, we have generating functions of this kind. zq to the k raised per alpha k, ak. And these he calls hands, decks, I don't know what he calls. So our ultimate goal is to generate something like this so that we can capture all. So this includes trees, and it includes, various kinds of objects. If you see Wilf's book, beyond the point where we left it, he considers generating functions and various objects of this generated by this kind of thing. And all this stuff gets covered here, so we can enumerate them. And then, I mean, the point here is that I want to show you some partition-like objects, and then some theorems from playing around with these M's. Okay. So any questions?